Up to now, we've been focused on looking at vector spaces, which are Rn or some subspace of Rn. But now I'm going to look at a different one. So this is the collection of matrices with m rows and n columns. So the m by n matrices. And notice that if you take two m by n matrices and you add them together, then you get another m by n matrix. And if you scalar multiply an m by n matrix, then you get another m by n matrix. So these form a vector space. And so in this case, the zero element looks like the matrix of all zeros here. So there's going to be m rows and n columns, but that's our zero element for this vector space. So let's just look at m sub n. So this is going to be n by n matrices. And so if we start off by looking at, say, m2, and I would ask you, well, let's take U to be all of the elements of, well, and since they're, we usually write these with capital letters, let's call them capital letters. All matrices of M2 which are, say, symmetric. Okay, then is U a subspace of M2? Well, let's see. So suppose we take B and C to be elements of U. Okay, well then what does that mean? Well, if they're coming from, the whole meaning of coming from this set U means that they are 2 by 2 matrices which satisfy this criterion right here. So that tells us that if we choose two things from here, then they both have this criterion. So B is symmetric and C is symmetric. Now you notice at this point here, I'm using the definition so that I can write down what it means as an equality, an equation. Okay, so now for scalar multiplication, I have to check B plus C. So the question is B plus C symmetric? And how do you answer that question? Well, you take its transpose and see what you get. And so the transpose, well, now we look for some way to manipulate this, and at some point it occurs to you, oh, well, we had a theorem that tells us I could distribute the transpose, and I don't know anything else about B and C other than the fact that that they're 2 by 2 matrices. So I don't know anything about their entries or anything else. All I know is that they're 2 by 2 matrices and symmetric. So somehow I'm going to have to use some basic property. Okay, so I know that I can at least say that this is equal to B transpose plus C transpose. And this is by some transpose theorem. And then let's see, well, what else do I know? Well, I chose B to be an element of U, so I have this equality, and C to be an element of U, so I have this equality, and so I can use both of those now. So I can replace this one with B and this one with C. Since I chose these to be symmetric matrices in the first place. And so now I look at where I started and where I finished, and this says that if I start with B plus C and take the transpose, I get back to B plus C, and that's exactly what it means to say that B plus C is symmetric. And if B plus C is symmetric, that's exactly the criterion for it being in U. So I know now that it's the symmetric matrices are closed under addition. What about if I take a scalar multiple? Actually, here, we'll just look at C times B. Okay, so to see whether or not this is symmetric, I need to take its transpose. But we also have some transpose rule that says that's equal to C times B transpose. And then we know that B transpose is equal to B because we chose B to be an element of U. We chose it to be symmetric in the first place. And now looking again from start to finish, if I take CB and I take its transpose, I get CB. And that's exactly what it means for CB to be symmetric. So if CB is symmetric, it's in U. So it's closed under scalar multiplication as well. So let's see, what about if I take V to be the, so the conclusion is that, so yeah, so U is a subspace of the 2x2 matrices. What if we let V be all those 2x2 matrices which are upper triangular? So maybe you can see just by thinking about it that this one's going to work out as well, but let's go through the steps. I didn't bother to check the 0 for this last one, but for this one, maybe I should. So let's just write down. So what does it mean to be an upper triangular matrix? That means if you're in here, then A has to look like A11, A12, 0, A22. So in other words, A21 has to equal 0. Okay, so for the 0 matrix, it is true that the 2-1 entry is equal to 0, so 0 is going to be an element of V. Okay, let's do addition. So let B and C be elements of V. Then that means that B21 is equal to 0 and C21 is equal to 0. So if I look at B plus C, then if I look at the 2-1 entry of B plus C, this is going to be B21 plus C21, which we just agreed was both of those were 0. So the sum is going to have a 0 in the second row, first column. And so then that means that it will also be an element of V. And if I look at a scalar multiple of B, then the 2-1 entry of that scalar multiple is going to be C times the 2-1 entry, because that's how we do scalar multiplication, which is C times 0 because we picked B to be from V. And so that shows you that C times B is also in V. So V is a vector space, and in particular, it is a subspace of M2.